Hello everyone, in this video I will talk about a sample problem on concrete mix design. It asks us to design a concrete mix for the following conditions and constraints. It's for a bridge pier exposed to freezing and subjected to de-icing chemicals. The required design strength, minimum dimension, minimum space between rebars, minimum cover over rebars are provided to you. And the standard deviation of compressive strength is 2.4 MPa. It's obtained based on experiments performed on more than 30 samples. And only air entrainer is used in the mix design, no other admixtures. For cement, we selected type 5 due to severe sulfate exposure. So before I talk about the other conditions and constraints, let me first briefly introduce the different types of Portland cement. So in the previous class, we talked about standard Portland cement, and there are actually 5 different types of standard Portland cement. The first type is called the normal type. It's the one we often use in general concrete structures. The second one is called moderate sulfate resistance cement. It's for protection against moderate sulfate exposure. The first type and the second type are widely available in the United States. The third type is called high early strength cement. It's used for fast track construction when forms need to be removed as soon as possible, or for structures that need to be put in service as soon as possible. And we often use it in cold weather. We want to reduce the time required for the curing process. For high early strength cement, the cement powders are finer because when the particles are finer, they have larger surface area, and so the hydration process will be faster and the strength is developed in a faster manner. The third type only occupies about 4% of the total cement production in the United States. The next one, the fourth type, is called low heat of hydration cement. It's used for large structures. So when we build large dams or large piers, we want to use the fourth type to have a more careful control of the heat generated during the hydration process. The last one, the fifth type, is called the high sulfate resistance cement. It's used for protection from severe sulfate exposure. So that's the one we used in this sample problem. So we selected type 5 due to the severe sulfate exposure. Next, the air entrainer, we get the specification from the manufacturer about how much we are going to use in the project. Also, the coarse aggregates, it's rounded river gravel and the nominal maximum size, bulk oven dry specific gravity, absorption, oven dry rounded density, and moisture content are provided to you. For fine aggregates, we use natural sand, and bulk oven dry specific gravity, absorption, moisture content, and fineness modulus are provided to you. Okay, so let's see the first step about how to determine the required strength. So we know the strength specified by the designer, FC prime, is 24.1 MPa. Also the standard deviation, it's given to us 2.4 MPa. And it's based on the experiments performed on more than 30 samples. So 2.4 MPa on more than 30 samples. Because we have enough number of samples to calculate the standard deviation, so we don't need any modification factor to modify the value of S. So we can directly use this value in our formula. So next, let's see how to calculate the required strength of CR prime. So we can check the previous slides about which formula we are going to use. So you see here, because we don't need multiplication factor, so we directly use S. So we can compare the value of S with 500 psi. So if it's less than 500 psi, we're going to use this formula. If it's more than 500 psi, we are going to use the second formula. So the standard deviation is 2.4 MPa, so which is equal to 350 psi. So it's less than 500 psi. So we want to use the first formula in the slide. So it's FCR prime equal to FC prime plus 1.34 times S. So it's FC prime plus 1.34 times S, so which is 24.1 plus 1.34 times 2.4. So if you calculate this value, it's 27.3 MPa. So this will be the required strength for this project.